Hello students, in last lecture we have seen the definition of G set. That is, G set is nothing but which is a mapping from G cross X to X, and which on this mapping we define where G is a group and X be any set, right? Then we define this mapping phi from G cross X to X as phi of A comma X is equals to A star X. And if this mapping defined in this way satisfy these two conditions, that is A star B star of X is equals to AB star of X, that is this closure is get applied here on A and B. And the second condition, that E star of X, that is when the element E act on X, that is the element of capital X, we get the element X. Okay, that is this two conditions satisfied for all the elements of the group, that is for all A comma B belongs to G and for all the elements in the set capital X. Then we can say that this G is acting on X, that is it applied on X, and this X with this operation is called as a G set, that is X is a G set. Okay, now in this video lecture we are going to see the definition, that is a stabilizer of a group, stabilizer. Then we see orbit, normalizer, and class of element, that is this class of the group in which we divide the given set into a partition. Okay, so let's see the definition first. So we see firstly the definition of a stabilizer of an element. Okay, so stabilizer is nothing but the set Gx which is equals to the set of all the element of the group such that Gx equals to X. That is, this we have here G is our group and capital X is our G set. That is, this G group is applied on this set X, and this X form a G set under the operation, that is A star of X is equals to AX. Okay, so here this Gx is nothing but our A star X, that is the operation applied on this G set X. Okay, so if it is equals to Ax, then it is translation. If it is equals to Ax A inverse, then it is conjugation. Okay, that we have seen in the example. Okay, so here only remember that this Gx is nothing but the operation which applied on the G set X. So what is a stabilizer? Stabilizer is the set of all element when applied to X, that is the element of capital X, will gives you itself X. Okay, so see here X equals to XYZ, that is it contains three elements. Then Gx, which is a stabilizer of X, this small x, that is this is a stabilizer of the small element X, is the set of all the group element which gives you itself X when applied on X. Okay, so this is a stabilizer of X. Similarly, we get stabilizer Gy, that is equals to the set of all the group element. We satisfy this condition that Gy is equals to Y. Therefore, this is a stabilizer of Y. Now, we can easily see that this Gx, that is the stabilizer, is a subgroup. And since it is a subgroup, therefore the stabilizer is a group of X in G. That is, stabilizer is a group. Since it is a stabilizer of X, therefore it is a group of X in G. Okay, we see the example of the stabilizer group as we have seen the examples of G set. So we take the G set and we find the stabilizer of that. Okay, so see in an example that let G be a group and H is normal subgroup of G. Then the set G by H of a left coset is a G set. that is this G by H. If we have H is normal subgroup, then G by H becomes a set of all left coset or right coset. Okay, so here we are taking the left coset. Now this G by H is a G set, that is, since H normal subgroup, therefore this form a G set. Okay, and this G set is a form if we define, that is, this is a G set if we define A star of X, that is the operation defined on this G by H. Since this is a quotient group, because H is normal subgroup, therefore the element of G by H will be of the form this left coset we are taken here. Okay, now since it is a G set, therefore we define the operation A star of XH is equals to AXH, where A belongs to G, and since XH is the element of the left coset, that is this quotient group G by H, right? So under this operation A star XH, this G by H is a G set. You can verify this from the given examples. Now we find here the stabilizer. Okay, so here the stabilizer of a left coset XH is the subgroup. As we have say that here the stabilizer is a subgroup. Okay, so we are saying here also that this left coset XH is the subgroup, that is stabilizer of this element, because this element will be element of G by H. Okay, so we are taking the stabilizer of this element XH is the subgroup, and which is equals to the set of all G belongs to G, such that G and the element will be, as here this X will be in the G set, so here we have the G set is G by H, so the element of this set is X into H, and that is equals to, we require this Gx equals to X. Okay, so Gxh we require this is equals to X into H, right? So this is equals to what? This set is equals to the set of all the element of G. Now we can take here this, we can multiply here by X inverse. So X inverse Gx into H is equals to, here if we multiply here XH by X inverse, so X inverse into X is E into H, and since E belongs to H, therefore EH is equals to H. Okay, so here X, after multiplying here, pre-multiplying by X inverse, we get on this right side we get H. Okay, so that is equals to the set of all G belongs to G, X inverse Gx into H. This is equals to H. What this implies, this X inverse G into X belongs to capital H. Since we know that AH is equals to H if and only if A belongs to H. Okay, so this is, since AH equals to H, we know that whenever this is equals to H, then A belongs to H. So here we have the equality, and therefore this X inverse Gx belongs to capital H. Okay, that is equals to what? This is equal to the set of all G belongs to G, such that now we can here multiply pre-multiplied by X and post-multiplied by X inverse. So we get G belongs to XH X inverse. Okay, so here after multiplying we get this element, right? So we have here, we have the set G belongs to G, so that G belongs to XH X inverse, and this is equals to what? That is, see here, this group is nothing but what? This is the element of all the G, that is the element of all the group, all the elements of group which belongs to XH X inverse also. Okay, so what is equals to this? This set is nothing but XH X inverse. So by observing this set is nothing but our XH X inverse. Okay, so here our stabilizer of the left coset XH is the set X into HX inverse. Okay, so here the stabilizer we get here is equals to this set XH X inverse. Now we see the definition of a normalizer. So if G acts on itself by conjugation, that is G is acting on itself, therefore G becomes a G set, and the action defined on G will be conjugation. Okay, so with this action, this G becomes a G set. Then for X belongs to G, the set. Okay, so when X belongs to G, we have the set Gx, that is equals to set of all A belongs to G such that Ax A inverse is equals to X. That is, this is our conjugation here defined on the G set. So Ax A inverse equals to X. We call this set as normalizer of X. That is, this set is called as the normalizer of X in G. So what is a normalizer? Normalizer is the set Gx, that is, it is the element of the group which satisfy Ax into A inverse, which gives you X, that is equals to Nx. Or we can write this set as Gx is equals to A belongs to G such that Ax is equals to X into A, that is equals to N of X. So normalizer of X is nothing but the set of all those elements which commute with this X. As you have seen here, Ax equals to Xa means X is commute with A, right? So what is the normalizer of the element X? Normalizer of this element X is the set of all the group elements which commute with this X. Okay, so to remember the normalizer set, we remember this condition, that is the set which is commute with all the elements of the group G. Now we see the definition of orbit of X in G. So what we define the orbit as, let G be a group acting on a set capital X, and let X belongs to capital X, then the set Gx, that is, we define the set Gx is equals to G, here we multiplied by X, is equals to the set of all the element in which we multiplied by, that is, we multiply all the elements by X of the group G. So what is the orbit? Orbit means when we multiply this all the element by X and we collect those elements, we get the set Gx. Then this Gx is called as the orbit of X in G. Is called the orbit of X in G. Okay. So what is the orbit is? Orbit is the set of all those elements we have multiplied here by the element of the group G by the element X. Okay. And this element, this set is called as the orbit of X in G. Now let's see the example of the orbit of X in G. Example, let G be a group and it is itself a G set by defining A star of X is equals to Ax. Okay, what this is called as? This is called as the translation action on G itself. Okay, so under this action where A belongs to G and X is also belongs to G. So under this action, what is the orbit? Orbit Gx is equals to the set of all Ax, that is this, the translation defined on this set G is Ax, where A belongs to G. But since we know that since A belongs to G and X belongs to G, okay, what this implies? A into X belongs to G. That is, this is a set of all the elements in a group G. Therefore, this set is equals to G. And thus we can say that the orbit G of X is equal to G itself. Okay. So, under the translation action on G, we have the orbit of X in G is the G set, that is G, the group G itself. Okay. We see one more example, that is second example on the orbit of X, that if G is a group and G, by defining, and on G we define the action as a conjugation. Okay, that is, under this action we have this G becomes a G set. Define the action as a conjugation, that is A star of X is equals to AX A inverse, where A belongs to G and X is also the element of G. So under this action, this G is a G set, and therefore for this G set we find the orbit, that is the orbit Gx. For X belongs to G, Gx, which is nothing but our orbit, is equals to what? It is the set of all Ax such that A belongs to G. As from the definition, the orbit is given in this way, Ax such that A belongs to G. Therefore, this is equals to Ax such that A belongs to G. But this Ax is nothing but our action defined on this G set. So here A star X, this is nothing but our Ax. Okay. So remember here, as here we have not defined the operation any between this Ax. So the operation between A and X is nothing but the action defined on a G set. Okay. So here Ax is nothing but our Ax A inverse. So this is nothing but our A star of X such that A belongs to G, and that is nothing but our Ax A inverse such that A belongs to G. And this is equals to the set of all B such that B is equals to Ax A inverse, where A is the element of G. That is, we write this Ax A inverse equal to B, and thus the set is equals to the set of all B where A belongs to G. And we denote this set by C of X. That is, Gx is nothing but our C of X. This is called as the class of X. Class of X means, or we can say that it is conjugate class of X. Okay. So orbit of X belongs to G, that is any element of G under the conjugation action which is defined on G itself is a conjugate class of the X, that is conjugate class of an element X. Okay, so let's see, from this we get this new definition of the class of X and the conjugate element. We see the definition of conjugate class and the conjugate element. Conjugate of element. So to define the conjugate of element, we let G be a group. Okay, if we have given G be a group, then and A comma B belongs to G and A comma B belongs to G be any two element, then B is said to be conjugate of A in G. That is, this B is called as the conjugate element of A in G if there exists X belongs to G such that B is equals to XA X inverse. That is, any element of this group G is written, that is, for this element B, B is said to be conjugate of A if there exists a element X belongs to G, which can be written in this form: B is equals to XA X inverse. That is, for every element B and A, are said to be conjugate if there exists the element which should be written in this form. Okay, or we can say that we write this conjugation in the notation form as A is conjugate to B or A is equivalent to B, where what is the meaning of this? B is conjugate to A. Okay, so when B is conjugate to A, we write A is equivalent to B and B is conjugate to A. For example, if we write X is conjugate to Y, what this means? X is equals to AX A inverse, AY A inverse. That is, there exists A belongs to G and we write this X in this way. Okay, so whenever this is written in this way, then we say that X and Y are conjugate element. Now if we consider the set of all those elements which is conjugate to B, then it form a class. Okay, so we define the definition that conjugate class of the element B, that is conjugate class of A. Okay, we take the conjugate class of A. That is, what is a conjugate class of A? It is the set of all those elements which is conjugate to A. Okay, so for A belongs to G, we define the set C of A. That is this C of A is nothing but, as here we have written the class of X as C of X. So here the class of A, that is the conjugate class of the element A, is the set of all the element of the group such that which is conjugate to A. Okay, so we have considered here the set of all those element of the group G which is conjugate to this element A, that is equals to the set B belongs to G such that B is equals to XA X inverse, because we have write the conjugate to B means what? B can be written in this form, XA X inverse. Okay, so A is equivalent to B means B is conjugate to A, and therefore by the definition B is equals to XA X inverse. And this is nothing but our, therefore we can write the set of all B belongs to G such that B is equals to XA X inverse, where X belongs to G, and therefore this is the set of all XA X inverse such that X belongs to G. Okay, so conjugate class of the element A is nothing but the set of all XA X inverse, that is element of this form, where X is the element of the group G. So this is called as the conjugate class of A. As here we have seen the conjugate class of an element, similarly we can see that conjugate of a set, conjugate class of set, okay, or conjugate of a set, which can be written in this form. Let G be a group and S be the set, that is S be taken as a subset of G. If X belongs to G, then the set X S X inverse is the set of all the element B such that S is equivalent to B. Okay, and S small s belongs to capital S. This is a small s. Okay, that is, this is a XS X inverse is the set of all B which are conjugate to every element of this S. What is the meaning of this set? Set of all those elements. This small s belongs to capital S. So it is conjugate to all the element of this capital S. That is set of all those elements which are conjugate to capital S, which we can write as B. S equivalent to B means what? B is equals to X S X inverse, where X is the element of G. That is equals to this S is small. Okay, that is this set X X X inverse such that S belongs to capital S. Okay, so we have multiplied here X and small x inverse to S. So it is the set of all X small s X inverse, where small s belongs to capital S. Okay, so this set is form a conjugate of the subset or conjugate class of a set. Okay, so now here our definitions were completed. In the next lecture we are going to use this definition to prove our theorems. Okay, and as we have seen here the conjugate class of A, so for every element we get the conjugate class of A. Okay, that is we get the for every element. For example, if G contains a finite element n elements, okay, and for this G we can define a conjugate classes for all the n1 n2, that is this n elements is nothing but our 1 2 and so on up to n. Okay, for example we have taken this 1 to up to n. Now for conjugate class of, for the 1, that is first element, we get here some conjugate class means the elements which are conjugate to 1. Then in the second class we get the element which are conjugate to 2. Then in the third class we get the element which are conjugate to 3. Okay, so if these are this conjugate class, that is this conjugate relation, that is this A equivalent to B, that is this conjugate relation is an equivalence relation. What this form? This is an equivalence relation. That is, it satisfies the property. What is an equivalence relation satisfy? It satisfies the property that first one is transitive, then second one is symmetric, and the third one is reflexive. Okay, or we can say that it is reflexive, symmetric and transitive. Transitive means first we see the reflexive, that is A is equivalent to A. Then we see the symmetric property that A is equivalent to B, then B is equivalent to A. When A is equivalent to B, then this implies B is equivalent to A. And the transitive is nothing but when A is equivalent to B and B is equivalent to C, then A is equivalent to C. Okay, so this relation, that is, this is a conjugation relation, that is B is written as AX inverse. Okay, therefore B and A are conjugate element. So this conjugate classes as defined here C of A, this conjugate classes, because of this equivalence relation, this conjugate classes partition the G, that is it partition the group G into an equivalent classes, that is it forms a classes of that is it forms a class, that is G can be written in the union of class of A where A belongs to G. Okay, that is it forms a partition, this partition G into an equivalence classes C of A, CL of A, where A is the element of the group G. What it means? Partition means what? We divide this set G into a partition, that is we can separate the element, and if we have the two classes, class of A and class of B, then the intersection of these two classes is empty, that is they are disjoint. What is the meaning of the partition? That if we have any two classes and if we take their intersection, then they are disjoint, that is their intersection should be empty. And if A is equivalent to B, then conjugate class of A is equals to conjugate class of B. Okay, that is if any two element of this class is equivalent, then conjugate class are also equivalent. Okay, so we see all this in detail in the next lectures. Thank you everyone.